Okay, question number 1.121. A body of mass m was slowly hauled up the hill, as shown in the figure, by a force F, which at each point was directed along a tangent to the trajectory. Find the work performed by this force if the height of the hill is h and the length of its base is L and the coefficient of friction is K. This is a nice spicy problem. Okay. So height of the hill is h, the length of the base is L. Okay. So there is no definite shape to this. Okay. And there is a mass m that is slowly hauled up the hill. Okay, that's important. Whenever you hear slowly hauled up, it means there was no change in kinetic energy. Okay, or there was no additional velocity that was added to the mass. Okay, so and this was hauled up by a force which is at any point tangential to the trajectory. Okay, all right. Okay, so the first up, we will be using work energy theorem. What does the work energy theorem tell us? Work done by all forces is change in kinetic energy. Okay. Now, what are all the forces that are acting on this mass m? Let's look at that. Let's say this is the mass. There is force of gravity acting downward. Okay. There is this force F acting tangential to the trajectory. Now, if this is, let's say, the trajectory, okay, perpendicular, so this is tangent at this point, perpendicular to that, there will be normal reaction from the surface of the hill, and we also have friction force acting opposite to the direction of motion. So friction force is also tangential then, okay? So these are all like perpendiculars, okay? Now then, let's come back to the work energy theorem. So work done by all forces, so work done by capital F plus work done by normal reaction plus work done by friction force plus work done by gravity should be equal to the change in kinetic energy. Now, because the mass was slowly hauled up, there is no change in kinetic energy, so this must be 0. Okay. Now, our goal is to find out WF. So, this is what? This is minus of work done by normal reaction plus work done by friction force plus work done by gravity. Okay. Now let's look at each of these individually. Normal force. Okay, let me write it down here. Now at any point, the normal force is at right angles to the displacement vector. Normal force is at right angles to the displacement vector. So work done by normal force will be what? 0. So we can eliminate this. Okay. Now let's look at gravity first. Okay. Now gravity is a conservative force. And what is a conservative force? A conservative force is one for which work done by the conservative force on any body is only dependent on the initial and final position and is independent of the path. So we can take work done by gravity from point A to point B and then from B to C instead of going along the hill. Okay? So if we do that, work done by gravity, we can write as work done in path AB plus work done in path BC. Now work done in path AB, mg is acting this side and displacement is at right angles, SAB, let's say. So this is again 0. And work done in path BC, mg is acting this side and displacement SBC is in the opposite side, which is given as height h. So this will be minus mgh. Also you could have interpreted this as work done by gravity is, or change in potential energy is negative of work done by a conservative force, and we know potential energy is due to gravity near earth is mgh, so work done by gravity is minus mgh. Okay, pretty simple. So we found this out. Now only thing that remains is work done by friction. Now how can we find out the work done by friction? Okay, let's look at that. Let us suppose at any point on the trajectory, let's say this was the trajectory again, okay, at any point on the trajectory, the friction force will be tangential to the trajectory and there will be a normal reaction which is perpendicular to the tangent and mg is acting vertically downwards. Okay. Now if I extend this, let us assume this angle is theta. Theta will be varying as we go along the trajectory, but at some point let us assume this angle is theta. Okay, so then what is n? Normal reaction is mg cos theta. So then what is friction at that point? Is the coefficient of friction is given as k. Coefficient of friction is given as k. So this is kn or k mg cos theta. Perfect. Now let us suppose that the body moved along the trajectory in a small distance ds. A small distance ds. Okay. Now what I will do is I will enlarge this part right here because I want to show you something. So the small distance ds, okay, if I draw a horizontal and if I drop a perpendicular, then this side is dy and let's say this side is dx. What is this angle, do you think? By plane geometry we can say the normal reaction was this side, the mg was acting perpendicular like this angle we defined as theta. So then it follows that because this is a 90 degree, it follows that this is 90 minus theta and this is a 90 degree, it follows that this angle is also theta. Okay. So then we can write ds cos theta will be a dx and dy will be ds sine theta. Okay. Now small work done by friction force in moving this distance ds is F dot ds, and F and ds are in the same direction. So we can actually write ds as dx by cos theta, F dx divided by cos theta. Now let's substitute F. F becomes k mg cos theta divided by cos theta. Cos theta gets cancelled out, it becomes k mg. Actually, I forgot the dx. We should have the dx there. Okay, kmg dx. Okay. Now, if you integrate both sides to find out the total work done by force of friction, the integral will be kmg dx. Now, while the body moves from A to C, what is dx? It is L, so from 0 to L. So work done by friction becomes kmg L. Okay. So now then, we found out work done by friction as well. Okay, one more thing. I made a mistake. The mistake is there should be a negative sign. Why? Because friction and displacement are in the opposite directions. So this should be minus. Okay. So now then the work done by the force F is minus of work done by friction, which is minus kmgl, and plus work done by gravity is minus mgh. So we can, minus minus gets cancelled out, we can take mg common, it becomes h plus kl. Okay, so that is our answer. Work done by the force F is mg h plus kl. Now, gravity is a conservative force, so we could do this. We could find out the work done in a more simpler path. But we couldn't do that for friction. Why? Because friction is a non-conservative force. And for non-conservative forces, the work done is dependent on the path. So we actually had to do the integral over the path, over ds. Now it so turned out that in this case, because we could reduce it to just doing a work done in the x direction, it worked out that way. Okay, but we cannot do the same shortcut like we did for gravity force.